I'm Mark Kavanaugh for Kavi Coaches, and today I'm going to coach you up on PV diagrams and the first law of thermodynamics. In this video, we're going to talk about PV diagrams and the first law of thermodynamics, which involves work, heat, and internal energy. So first, we're going to define what the system is going to be for these types of questions. So our system is going to be defined as the gas. So a gas that's in an enclosed container. The boundary is the sides of the container, and the boundary serves some purposes. It does not let mass in or out. It may or may not let in heat, and it may or may not let the piston compress or expand the gas. The environment is anything that's outside of the enclosed container. So any air outside, the warm air, the piston itself, all of the things that are not part of the gas are considered the environment that can transfer energy to or from via working or heat. So let's go through some vocabulary first. So we're going to start with an isothermal process. So if we break that word down, thermal, usually thermal has to do with temperature, and in this case it does. So temperature is what's going to be constant in this case, where pressure and volume are going to change. So what does an isothermal process look like? Well, we know that pressure and volume are an inverse relationship. So the graph is going to be an inverse relationship. So you can see here we have a temperature that does not change along this curved path. So we'll call that T1. And we're going to draw a couple other curves to represent T2 and T3. And we can see that those temperatures are different temperatures, but the same along each of those lines. Now, if we look at a position from A to B along that curved path, we know that from A to B, the temperature does not change, but we know that from A to B, that the volume increases, so the pressure decreases. And from B to A, the pressure increases, so the volume decreases. So it depends which direction we're going. So what does that look like for the gas? So if this was position A, where we're starting, we know that the volume expands, so the volume gets larger. It's an isothermal process, so the temperature stays the same. So therefore, the pressure has to decrease. So if you think about if we increase the volume with the same motion of particles, that means they're going to have to travel further to hit the sides of the container. So it's a lesser pressure because there's less collisions with the sides of the container. And we saw what it looks like for our PV diagram, the isothermal process, that inverse relationship going from A to B, the volume increased and the pressure decreased. The next term we're going to define is an isobaric process. Isobaric is like barometric pressure, and that's what it means, is pressure. So the pressure is going to remain constant, and volume and temperature are going to change. And we know from the previous video that volume and temperature are a direct relationship. So the pressure remaining constant means we're going to draw a horizontal line. So if the volume increases, we know that T1 and T3, that's an increase in temperature. To go from T3 to T1, that is a decrease in temperature and a decrease in volume. They're both directly related. So an isobaric process is going to be a horizontal line drawn on a PV diagram graph. So what does that look like for our gas? So position A, we have the pressure is staying the same. So if the volume expands and the isobaric process shows that the pressure remains the same, well, if the volume gets larger, direct relationship, that means the temperature has to increase. So the gas is going to increase to be able to have the same number of collisions with the sides of the container. The molecules have to move further, have the same number of collisions. So in order for that to happen, they have to be moving faster. On our PV diagram, we looked at that, and to go from one temperature and one volume to another is a horizontal line at a constant pressure. So this would be an increase in volume and an increase in temperature. So T3 is a higher temperature than T1. An isobaric process from position C to position D, we know the volume contracts, the pressure remains constant, so that means that the temperature is going to have to decrease because the volume and temperature are directly proportional. So the temperature has to cool down. On our PV diagram, this is a horizontal line that points to the left. So it does matter the direction on the PV diagram if it goes from C to D or D to C. The volume and the temperature dictate which direction that's going to travel. Our third process is an isovolumetric or isochoric process. The first word obviously talks about volume, but you're probably most likely going to see isochoric as the type of description for the problem. So know that isochoric means that volume is constant. So pressure and temperature are what's changing. So the volume being constant and pressure and temperature changing, pressure and temperature are a direct relationship. So as the pressure drops, that means the temperature is going to drop as well. So we have a vertical line showing that the volume doesn't change. So that piston is locked into place and not allowed to move. And if we go from C to D moving upward, that means as the temperature increases, the pressure is going to increase. So the temperature is what's going to dictate the pressure. So at position A, we have a warm temperature, and we know that it has the same volume, so we've locked that piston in place. So the temperature decreases, causing the overall pressure to decrease because there's going to be less collisions with the sides of the container. The molecules are moving slower, so therefore not as many collisions with the sides of the container, meaning that there's going to be a lesser pressure. On our PV diagram, what that looks like is a vertical line from one temperature to another, causing the pressure to decrease as the temperature drops from T3 to T1. What does that look like for position C to position D? Well, the temperatures increase, so the gas is warmer. The volume stays the same because it's isochoric. So if the volume stays the same and the temperature increases, there's more collisions with the sides of the container because the molecules are moving faster. On our PV diagram, that looks like a vertical line going from, in this case, T2 to T3 along that path from C to D. So our fourth process is called an adiabatic process. So on this curve, we're just using the isothermal line as a reference point for what an adiabatic process looks like. So an adiabatic process is a much steeper curve, and this curve does not allow any heat to be transferred between the environment and the system. So if we have an adiabatic compression, that means the volume is going to be decreasing. And that's going to be moving in this direction, kind of upward, which means that the temperature is going to increase, the pressure is going to increase, and the volume is going to decrease. So all three things are changing. And an adiabatic expansion would be the opposite. Pressure decreases, temperature decreases, but volume increases. Now, an adiabatic process is a very quick, rapid change in volume to cause pressure and temperature to change. So much like the piston in a car engine that rapidly moves up and down to contract and expand the volume of that cylinder. So let's recap the thermodynamic process. So we're going to look at the main three that we're going to look at. The isothermal process means there's no temperature change. And on a PV diagram, depends the direction. Remember to draw an arrow to represent. So this would be the volume decreasing and pressure increasing. And then we can flip that around, and then the volume increases and pressure decreases, but the temperature remains the same along that curve. Our second is isobaric, which means there's no change in pressure, and no change in pressure is a horizontal line along the PV diagram. And remember, draw an arrow to show the direction. If it goes from A to B, we draw an arrow from A to B, and the same thing from C to D, so horizontal line. Isovolumetric or isochoric means no change in volume. And on a PV diagram, that's going to be a vertical line. Again, make sure you draw your arrows to show the direction, either from A to B and then from C to D. So isochoric means that there's no change in volume. So let's look at internal energy, heat, and work in the first law of thermodynamics. So let's define first what each of those are. Internal energy is the energy of the atoms and molecules of a system of gas. The energy of a monatomic ideal gas is translational, and thus the sum of the kinetic energy of all the particles. So we'd add up the kinetic energy of all the particles. Not all particles are going to be moving at the same speed, so they'd have different kinetic energies, but the sum of them is going to be the total internal energy. They're directly related to temperature because as temperature goes up, the molecules move faster. Therefore, faster molecules means more kinetic energy. Heat is the transfer of energy between a system to or from the environment because of a temperature difference. And so if there's a difference in temperature, if we take a container of gas and put it in a freezer, the temperature difference would be transferring energy out. If we put it in a vat of boiling water, then the temperature would be hotter outside, transferring energy into the container of gas. Lastly is work. That is an energy transfer from a system to or from the environment via that movable piston in the form of mechanical energy, kinetic energy, because the piston is moving. So the work being transferred to the piston causes the piston to move either up or down, contracting or expanding the volume of that container. So that is the work that is done on the container. So let's talk about some vocabulary. The key word here is on. The work done on a system. So we have this gas is applying a force, expanding that volume. So the gas is pushing that piston upward. And that piston being pushed upward, it moves a distance that we'll call d. And we know from physics 1 that work is equal to force times distance. So that force that's applied times the distance is going to give us the work. Now that force is transferring energy to the piston. So therefore the system loses energy because the piston gains energy. So we're going to make that work value negative. Now we also know that the piston in 3 dimensions has a cross-sectional area of, we'll call it A. And we know that force is just pressure times area. So we can substitute P times A in for force. Now we also know that that cross-sectional area times the change in distance, well, that's just going to give us a change in volume. So work can be calculated by the negative pressure times the change in volume. And that's how much work is done on the gas. Now note that the pressure is constant as the work is done on the system. Now, if we have work done on the system, in this case, the force is greater, the net force is greater from the environment, well, that's going to cause the piston to contract and make the volume smaller. So we move that same distance d, but now we know that the work done on the system, the piston is now transferring energy to the system, and the work equation, since we know that work is equal to negative P times delta V, the change in volume decreases, so that's going to be a negative value. The negative change in volume means we have a double negative, which gives us a positive value for work done on the system. Now we're going to talk about, you'll see another word, the work done by a system. So everything that's written on your equation sheet is geared towards work done on. But now we're going to talk about work done by a system. So this is associated with the energy of the environment. So that's the piston and the surrounding gas, not in the container. This value is the opposite of the work done on the gas. So you can calculate the work done on the gas and then just change the sign. So the work done on a system is this equation. And an easy way to remember this is the work done on a system. This is the formula that is on your formula sheet. So that's the work done on a system. If we transition to the work done by the system, we say by to the negative sign. So the work done on a system is the equation on your formula sheet. The work done by a system, we wave goodbye to the negative sign. So the first law of thermodynamics ties together internal energy, heat, and work. And the equation is the change in internal energy is equal to heat plus the work. So delta U is the change in internal energy of a system. Q is the heat added to the system, and that can be negative if heat is transferred out of the system. And W, as we talked, is the work done on the system. So that can be positive or negative based on what's happening to the energy of the gas. So if we look at this with the system in the box, the first law of thermodynamics, if we transfer energy in via working, the work is a positive value, and if heat doesn't change, that means that delta U is going to have the same change as the work. If we have a temperature difference between the outside is warmer, that's going to transfer heat inside, and that's going to increase the internal energy if there's no work that's done on the system. Take energy out, what does that look like? Well, work done by the system to push that piston up, transferring energy to the piston. So the work done by the system means that there's going to be a negative value of the work done on the system. Same if there's warmer temperature for the gas inside than out, then there's going to be heat transferred out. So Q is also going to be negative when we have a transfer of heat out of the system. So if we look at a PV diagram, if we have work done at a constant pressure, that looks like our graph that we saw earlier in the video is a horizontal line from A to B. Now, the pressure times volume is the way we calculate work, the negative pressure times volume, which is also just going to be the area underneath this curve. Now, the problem with finding the area is you've got to determine, is that area going to be positive or negative? When the volume expands, it's going to be a negative value. When the volume contracts, it's going to be a positive value. So you have to make sure that when you find the area, assign the correct sign with either being negative or positive if it expands or contracts. So if we go from C to D, we can see that that doesn't take as much work. So because it's at a lower pressure, so the lower the pressure takes a lesser amount of work, and in this case, a lesser negative amount of work. So we can see that based on the areas, the absolute value of the work from A to B is going to be greater than the absolute value from C to D. Even though that value from A to B is negative and same for C to D, the absolute value is going to be greater. Now, work is path dependent. So we take these same 4 points, A, B, C, and D, and we take a process that is isobaric and then isochoric. We can see that we go from A to B to D, and that area is going to give us the work that is done. But we can also take that same process from A to D and go A to C to D, and we can see that that's going to take less work. So we can do the isochoric process first and then the isobaric process to go from A to C to D. And the absolute value of the work done from A to B to D is going to be greater than the work done from A to C to D. And the reason for that is because the area is going to be less. The work that's done is done at a lower pressure. So remember, work done at a constant pressure is the equation work equals negative P times delta V. And that area represents the work, and you have to decide positive or negative based on if the volume expands or contracts. So if we look at processes for the first law of thermodynamics, an isothermal process means there's no change in temperature, which means no change in internal energy. So that means the first law of thermodynamics just shows that work is equal to the negative of the heat that is done. So if there's a positive work, there's a negative amount of heat, and vice versa. For work, an isochoric process has work done is 0. That's a vertical line on the graph. So that means that the change in internal energy is directly related to the heat that is removed or added to the system. And our third process for the first law of thermodynamics is an adiabatic process, which we saw briefly earlier in the video. And that has a heat value that's 0, so there's no heat transfer. So that means delta U is directly equal to the work value. So if there's an increase in work, that means there's an increase in internal energy. So here's a recap of what we can look at from the first law of thermodynamics. So this is an introduction to PV diagrams in the first law of thermodynamics. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below and subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.